In the name of Allah, the Gracious, the Merciful. Welcome to the Operating System Series Part 1 in the System EC channel with you, Muhammad Nimr. The content of this video. In this video, we will talk about the operating system functions, computer system organization, computer system architecture, operating system structure, operating system operations, process management, memory management, storage management, protection and security, kernel data structure, computing environments, open source operating systems, summary, exercises, and notes. First, the operating system functions. The computer system is divided into four basic components: hardware, operating system, application programs, and users. The hardware is such CPU, memory, input-output devices, which provides the basic computer resources for the system. Application programs such as Word, Excel, compilers, web browsers, games describe the methods in which these resources are used to achieve the user computing requirements. The operating system controls the hardware and coordinates its use among a variety of application programs for variety of users. The operating system functions. The operating system consists of computer hardware, then the operating system. After that, the system and application programs, as shown here in this picture, where the user 1 is dealing with a compiler, and user 2 is dealing with assembler, and user 3 is dealing with the text editors, and also user n is dealing with a database systems. All these is a system and application programs. The operating system functions computer system. We can divide it also into hardware, software, and data. Operating system provides the means for proper use of these resources inside the operation of the computer system. Operating system is like a government, where it doesn't do a useful thing by itself, but it provides the appropriate environment within which the other programs can do useful work. Now, the operating system views. First, the user view. Users see computers in many ways, according to the interface being used. Most users use a PC, which consists of monitor, keyboard, mouse, and a system unit that monopolize these PC resources. The goal is to maximize and achieve successfully the user tasks. Here, the OS is designed for ease of use, enhanced performance, and resource utilization. Such systems are designed for the single user than the multiple users. When users use a terminal connected to the mainframe or main computer, in this case, other users are using the same computer but through a different terminals. These users share resources and may exchange information. Here, the OS is designed for maximizing the resource utilization in order to make all available CPU time, memory, and input-out be used efficiently, where no individual user takes more than his fair share. The user view is the case of workstation connected to networks of other workstations and servers. These users have dedicated resources at their disposal, but they also share resources as networking and servers. Sharing is also including files, computing, and print servers. The OS here is designed for compromise between the individual usability and resource utilization. For mobile computers such as smartphones and tablets, these devices come into fashion. Most of it are standalone for individual users. Often, they are connected to networks through cellular or other wireless technologies. These devices is preferred for users who primarily using computers for email and web browsing, rather than desktop and laptop. The user interface here features a touch screen generally. The user interacts with the system by pressing and swiping fingers. The computers which have little or no user view. These devices is such as embedded computers in home devices. Also in automobiles which may have numeric keypads and may turn indicator lights on or off to show status. The OS here is designed basically to run without user intervention. Now the system view. Now we will explain the OS from the computer's point of view. The OS here is a program which is most intimately involved with the hardware. The OS is such as a resource allocator. The computer system has many resources that may be required to solve problems, such CPU time, memory space, file storage space, and input-output devices. The OS acts as the manager of these resources. Also, OS decides how to allocate resources to specific programs and users so that it can operate the computer system efficiently and fairly. The resource allocation is very important when many users access the same mainframe or many computer. Also, there is a slightly different view of the operating system, where it emphasizes the need to control the various input-output devices and user programs. Also is a control program that manages the execution of user programs to prevent errors and improper computer using. This view is especially related to the operating or operation and control of the input-output devices. The operating system defining. The term operating system covers many rules and functions. It's already due that cause of the myriad designs and uses of computers. Computers are present within toasters, cars, ships, spacecraft, homes, and also within businesses. Computers also are the basis for game machines, music players, cable TV turners, and industrial control systems. It have a relatively short history, despite that they have evolved rapidly. Firstly, computers started as an experiment to determine what could be done, but it moved quickly to be a fixed purpose systems in order to use in military fields such as census calculation. The early computers evolved into general purpose, such as multifunction mainframes, in which the operating system is born. The computers gained in functionality and shrunk in size, and that leading to a vast number of uses and also a vast number of operating systems. The OS exists because it offers a reasonable way to solve the problems of creating a usable computing system. The basic goal of computing system is to execute user programs and to make solving the user problems easier. Also, the computer hardware is constructed toward this goal. As the hardware alone is not easy to use, application programs are developed. These programs require certain common operations, such as the operations of controlling the input output devices. The operating system becomes a piece of software which gathers the common functions of controlling and allocating resources. The OS until now has no accepted universally unified definition for its parts and components. The features included in the OS vary greatly across systems. Some systems take up less than megabyte of space, whereas others require gigabytes of space, and based entirely on GUI systems. A more common definition for the operating system is the OS is the program running at all times on the computer, usually called the kernel. Also, there are two other parts along with the kernel. They are first, the system programs, which are associated with the OS but are not necessarily a part of the kernel. Second, application programs, which include all other programs that are not associated with the operation of the system. As personal computers became widespread, the operating systems grew increasingly sophisticated. The number of features constituting the operating system is increasing. The mobile operating systems often include not only a core kernel, but also a middleware, which is a set of software frameworks that provide additional services to application developers. For example, the Apple iOS and Google's Android features a core kernel along with middleware that supports databases, multimedia, and graphics. Now, with a general knowledge of the computer system structure, with the operating system organization, computer system operation. The modern general purpose computer systems consists of one or more CPUs and a number of device controllers, which are connected through a common path that provides access to shared memory. In this picture, there is a shared memory and CPU, disk controller, which connected with disks, USB controller connected with mouse, keyboard, printer, and the graphics adapter connected with monitor, all of them connected with a shared memory. The computer system operation. Each device controller is in charge of a specific type of device. These devices is such as a drivers, audio devices, or video displays. The CPU and the device controllers can execute in parallel, competing for memory cycles. The memory controller synchronizes access to the memory to ensure orderly access to the shared memory. To start running the computer, it needs to have an initial program. This initial program is called also the bootstrap program, and it tends to be simple. Also, this program is stored within the computer hardware in the ROM or in the EEPROM, which is known by firmware. The bootstrap program initializes all aspects of the system, from CPU registers to device controllers to memory contents. Also, this bootstrap program must know how to load this operating system and how to start executing this system. To accomplish this goal, the boot program must to locate the operating system kernel and then load it into memory. Once this kernel is loaded and executing, it can start providing services to the system and its users. Some services are provided outside of the kernel by a certain system programs that are loaded into memory at boot time. These programs become a system processes or system daemons. The system daemons are a programs that run all the time as long as the kernel is running. On Unix systems, the first system process from these programs is called init, and it starts many other daemons. After this phase is completed, the system now is fully booted, and also the system waits for some events to occur. The hardware or the software is usually interrupted and causes the occurrence of these events. Hardware may trigger an interrupt at any time by sending a signal to the CPU, and usually through the way of the system bus. Also, software may trigger an interrupt by executing a special operation, which is called system call or monitor call. When the CPU is interrupted, it stops what it's doing and immediately transfers execution to a fixed location. The fixed location is an address that usually contains the starting address where the service routine for the interrupt is located. The CPU executes the interrupt service routine, and after completed, it resumes the interrupted computation which was running before. This picture shows the interrupt timeline for a single process doing output, which there is a CPU and input-output device, and there is user process executing above and input-output interrupt processing, and there is idle state and transferring state. When the input-output request, the CPU executes it, and then when transfer done, the CPU completed the user process executing. After that, the input output request again comes. Then the CPU interrupt and execute it, and after that, finally, the transfer done, and the CPU again return to the user process executing. Interrupts are an important part of the computer architecture. Each computer design has its own interrupted mechanism, but there are several interrupts functions that are common for all designs. The interrupt must transfer the control to the appropriate service interrupt service routine. There is a straightforward method to handling this control transfer, which is by invoking a generic routine to examine the interrupt information. The routine in his turn will call the interrupt specific handler. However, interrupts must be handled quickly. Only a predefined number of interrupts is possible. A table of pointers to interrupt routines can be used instead to provide the necessary speed. The interrupt routine is called indirectly through this table with no intermediate routine needed. Generally, the table of pointers is stored in low memory, the first 100 or so locations. These locations hold the addresses of the interrupt service routines for the various devices. This interrupt vector or array of addresses is then indexed by a unique device number, which is given with the interrupt request, and that to provide the address of the interrupt service routine for the interrupting device. Operating systems as different as Windows and Unix dispatch interrupts in this manner. The interrupt architecture must also save the address of the interrupted instruction. Many old designs simply stored the interrupt address in a fixed location or in a location indexed by the device number. More recent architectures store the return address on the system stack. When the interrupt routine needs to modify the processor state, for example by modifying register values, then it must explicitly save the current state and then restore that state before returning. After the interrupt is serviced, the saved return address is loaded into the program counter, and then the interrupted computation resumes as though the interrupt hadn't occurred. As the CPU can only load the instructions from memory, so any programs that need running must be stored there in the memory. Most of recent general purpose computers run most of their programs from rewritable memory, which called main memory, also called RAM. Nowadays, the main memory or RAM is commonly implemented in a semiconductor technology, which called DRAM or dynamic RAM. The computers use also other forms of memory as well. We've mentioned before the ROM and the EEPROM, where the ROM cannot be changed, so only the static programs, such as the bootstrap program, are stored there. The immutability of ROM is of use in game cartridges. The EEPROM can be changed, but cannot be changed frequently, and so it contains mostly static programs also. For example, the smartphones have EEPROM to store their factory installed programs. All forms of memory provide an array of bytes, where each byte has its own address. Interaction is achieved through a sequence of load or store instructions to a specific memory addresses. The load instruction moves a byte or word from the main memory to an internal register within the CPU, whereas the store instruction moves the content of the CPU register to the main memory. Also, the CPU automatically loads the instructions from the main memory for execution, and that is aside from explicit loads and stores. Now, with a typical instruction or execution cycle, as executed on a system and that with a von Neumann architecture, where in the von Neumann architecture first fetches an instruction from memory and then stores it in the instruction register at the CPU. This instruction is then decoded and may cause operands to be fetched from the memory and stored in some internal register. After the instruction on the operands has been executed, the result may be stored back in memory. Notice that the memory unit sees only a stream of memory addresses, where the memory doesn't know how they are generated, whether by the instruction counter, indexing, indirection, literal addresses, or by some other means, or even what they are for, instructions or data. Accordingly to what we have mentioned, we can ignore how the memory address is generated by a program. Here, we are interested only in the sequence of memory addresses, which is generated by the running program. Ideally, we want the programs and the data to reside in main memory permanently. This arrangement usually is not possible for the following two reasons. First, the main memory is usually too small to store all the needed programs and data permanently. Second, the main memory is a volatile storage device that loses its content when power is turned off or otherwise lost causes. And thus, most computer systems provide secondary storage, which is used as an extension of the main memory. The main requirement of this secondary storage is that it be able to hold large quantities of data permanently. The magnetic disk is the most common secondary storage device. It provides storage for both programs and data. Most programs, whether system and applications, are stored in a disk until they are loaded into memory. Many programs then use the disk as both the source and the destination of their processing. Hence, the disk storage proper management is of the central importance to a computer system. However, there are also many possible storage systems other than the register's main memory and magnetic disks. The other storages include cache memory, CD-ROM, magnetic tabs, and so on. Each storage system from those provides the basic functions of storing a datum and holding this datum until it's retrieved at a later time. The main differences between these storage systems lie in the speed cost, size, and volatility. The wide variety of storage systems can be organized in a hierarchy according to the speed and cost. Where the higher levels are expensive, but they are the fastest. As we move down this hierarchy, the cost per bit is generally decreases, whereas the access time generally increases. In this picture, the highest level is the registers, then the cache, and then main memory. After that, the solid state disks, then the magnetic disks, and the optical disks, and the slower ones is the magnetic types. We still with the storage structure. This trade-off is reasonable if a given storage system were both faster and less expensive than another. Then, there is no reason to use the slower, which is more expensive. In fact, many early storage devices, including paper tab and core materials, are relegated to museums. Now, the magnetic tab and the semiconductor memory have become faster and cheaper. The top four levels of memory in the previous figure may be constructed by using the semiconductor memory. The various storage systems are either volatile or non-volatile, and this is in addition to differing in speed and cost. The volatile storage loses its contents when the power to the device is removed. In the absence of expensive battery and generator backup systems, data must be written to a non-volatile storage for safekeeping. In the previous figure, the storage systems above the solid-state disk is volatile, whereas those below the solid-state disk and also including it are non-volatile. The solid-state disks have several variants, but in general are faster than the magnetic disks and are non-volatile. One type of the solid-state disks stores the data in a large DRAM array during normal operation, but also contains a hidden magnetic hard disk and a battery for backup power. If the power is interrupted, this solid disk's controller copies the data from the RAM to the magnetic disk. When the external power is restored, the controller copies the data again back into the RAM. Another type of the solid state disk is the flash memory, which is popular in cameras, personal digital assistants (PDAs), in robots, and increasingly for storage on general purpose computers. The flash memory is slower than DRAM, but needs no power to retain its contents. The NVRAM is another form of a non-volatile storage, which is a DRAM with a battery backup power. So the NVRAM is as fast as the DRAM, as long as the battery lasts and is non-volatile. The design of a complete memory system must balance all the factors just discussed. It must use only as much expensive memory as necessary, while providing as much inexpensive non-volatile memory as possible. Caches can be installed to improve performance, where a large disparity in access time or transfer rate exists between two components. Now with the input-output structure. The storage is only one of many types of the input-output devices within a computer. A large portion of operating system code is dedicated to managing the input-output devices because of its importance to the reliability and performance of the system. Also because the varying nature of the devices. Now, we will provide an overview of the input-output devices. A general-purpose computer system consists of CPUs and multiple device controllers, which are connected through a common path. Each device controller is in charge of a specific type of device. Depending on this controller, more than one devices can be attached. For instance, 7 or more devices can be attached to the small computer system interface or SCSI controller. A device controller maintains some local buffer storage and a set of special purpose registers. The device controller is responsible for moving the data between the peripheral devices that it controls and its local buffer storage. Typically, the operating systems have a device driver for each device controller. This device driver understands the device controller and provides the rest of the operating system with a uniform interface to this device. To start an input-out operation, the device driver loads the appropriate registers within the device controller. The device controller, in turn, examines the contents of these registers to determine what action to take, such as read a character from keyboard. The controller then starts to transfer data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. The device driver then returns control to the operating system, possibly returning the data or a pointer to the data if the operation was a read. For the other operations, the device driver returns status information. This preceded form of interrupt-driven input-output is fine for moving small amounts of data, but it can produce high overhead when used for bulk data movement, such as the disk input-output. The DMA, or Direct Memory Access Technology, is used to solve this previous problem. After setting up buffers, pointers, and counters for the input-output device, the device controller transfers an entire block of data directly to or from its own buffer storage to memory with no intervention by the CPU. And only one interrupt is generated per block to tell the device driver that the operation has completed, rather than the one interrupt per byte which is generated for low-speed devices. While the device controller is performing these operations, the CPU is available to accomplish other work. Some other high-end systems use switch rather than path architecture. On these systems, multiple components can talk to other components concurrently, rather than competing for cycles on a shared path. In this previous case, the DMA is even more effective. There is a figure shows the interplay of all components of the computer system. This figure is for how a modern computer system works. There is a thread of execution or CPU which has a cache and a specific device which dealing with the CPU uh, through input out request from the CPU and exchanging data between the device and the CPU, and also an interrupt from the device to the CPU. There's a technology or a way that's called the DMA between the device and the memory on the right side, and the instructions and the data being executed or being exchanging between the CPU cache and the memory. So the data movement is exchanging between the memory and the CPU for the for a bulk. After that, the CPU executes the input-output instruction. The computer system architecture. Previously, we introduced the general structure of a typical computer system. The computer system can be organized in a number of different ways, which we can categorize roughly according to the number of general purpose processors used. First, the single processor systems. Until recently, most computer systems used a single processor. On this single processor system, there is one main CPU, which is capable of executing a general purpose instruction set, including instructions from user processes. Almost all single processor systems have other special purpose processors as well. They may come in the form of device specific processors, such as disk, keyboard, and graphics controllers. Also, on mainframes, they may come in the form of more general purpose processors, such as the input output processors that move data rapidly among the components of the system. All of these special purpose processors run a limited instruction set and don't run user processes. Sometimes they are managed by the operating system, in that the OS sends them information about their next task and monitors their status. For instance, the disk controller microprocessor receives a sequence of requests from the main CPU and implements its own disk queue and scheduling algorithm. This arrangement relieves the main CPU of the overhead of disk scheduling. PCs contain a microprocessor in the keyboard to convert the keystrokes into codes to be sent to the CPU. In other systems or circumstances, the special purpose processors are low level components which built into the hardware. The OS cannot communicate with these processors. They do their jobs autonomously. The use of special purpose microprocessors is common and doesn't turn a single processor system into a multiprocessor system, where if there is only one general purpose CPU, then the system is a single processor system. Second, the multiprocessor systems. Within the past several years, the multiprocessor systems, also which known as parallel systems or multi-core systems, have begun to dominate the landscape of computing. Such systems have two or more processors in close communication, sharing the computer bus and sometimes the clock, memory, and peripheral devices. Multiprocessor systems first appeared prominently in servers and have since migrated to desktop and laptop systems. Recently, multiple processors have appeared on mobile devices such as smartphones and tablet computers. Multiprocessor systems have three main advantages. One, increased throughput by increasing the number of processors, which expect to get more work done in less time. But the speed up ratio with M processors is not M. However, rather it's less than M. When multiple processors cooperate on a task, a certain amount of overhead is incurred in keeping all the parts working correctly. This overhead plus contention for shared resources lowers the expected gain from additional processors. Similarly, M programmers working closely together don't produce n times the amount of work a single programmer would produce. 2. Economy of scale. The multiprocessor systems can cost less than equivalent multiple single processor systems because they can share peripherals, mass storage, and power supplies. If several programs operate on the same set of data, it's cheaper to store those data on one disk and to have all the processors share them than to have many computers with local disks and many copies of the data. 3. Increased reliability. where if functions can be distributed properly among several processors, then the failure of one processor will not halt the system, only slow it down. If we have 10 processors and one fails, then each of the remaining 9 processors can pick up a share of the work of the failed processor. Thus, the entire system runs only 10% slower rather than the failing altogether. Increased reliability of a computer system is crucial in many applications. The ability to continue providing service proportional to the level of surviving hardware is called graceful degradation. Some systems go beyond graceful degradation and are called fault tolerant because they can suffer a failure of any single component and still continue operation. Fault tolerance requires a mechanism to allow the failure to be detected, diagnosed, and if possible, corrected. The HB non-stop formally tandem system uses both hardware and software duplication to ensure continued operation despite faults. The system consists of multiple pairs of CPUs working in lockstep. Both processors in the pair execute each instruction and compare the results. If the result differ, then one CPU of the pair is at fault, and both are halted. The process that was being executed is then moved to another pair of CPUs, and the instruction that failed is restarted. This previous solution is expensive since it involves special hardware and considerable hardware duplication. The multiple processor systems in use today are of two types. Some systems use asymmetric multiprocessing, in which each processor is assigned a specific task. A both processor controls the system. The other processors either look to the both for instruction or have predefined tasks. This scheme defines a both worker relationship. The both processor schedules and allocates work to the worker processors. The amount common systems use is symmetric multiprocessing or SMP, in which each processor performs all tasks within the operating system. The SMP means that all processors are peers. No boss worker relationship exists between processors. There is a figure illustrates a typical SMP architecture. Notice that each processor has its own set of registers, as with as a private or local cache. This figure 1.6 for symmetric multiprocessing architecture. There is a three CPUs, CPU 0 and CPU 1 and CPU 2, and each CPU has its own registers and cache, and all the three CPUs are connected with a shared memory as shown in this figure. However, all processors share physical memory. An example of an SMB system is the AIX, or a commercial version of Unix, which is designed by IBM Corporation. An AIX system can be configured to employ dozens of processors. The benefit of this model is that many processes can run simultaneously. N processes can run if there are n CPUs without causing performance to deteriorate significantly. However, we must carefully control the input output to ensure that the data reach the appropriate processor. Also, since the CPUs are separate, one may be sitting idle while another is overloaded, resulting in inefficiencies. These inefficiencies can be avoided if the processors share certain data structures. A multiple processor system of this form will allow processes and resources such as memory, memory to be shared dynamically among the various processors and can lower the variance among the processors. Virtually all modern operating systems, including Windows, Mac OS, and Linux, now provide support for SMP. The difference between symmetric and asymmetric multiprocessing may result from either hardware or software. Special hardware can differentiate the multiple processors, or the software can be written to allow only one boss and multiple workers. For instance, Sun Microsystems operating systems Sun OS version 4 provided asymmetric multiprocessing, whereas version 5, which is Solar's, is symmetric on the same hardware. Multiprocessing adds CPUs to increase computing power. If the CPU has an integrated memory controller, then adding CPUs can also increase the amount of memory addressable in the system. Either way, multiprocessing can cause a system to change its memory access model from uniform memory access UMA to a non-uniform memory access NUMA or NUMA. The UMA or UMA is defined as a situation in which access to any RAM from any CPU takes the same amount of time. With NUMA, some parts of memory may take longer to access than other parts, creating a performance penalty. Operating systems can minimize the NUMA penalty through resource management. A recent trend in CPU design is to include multiple computing cores on a single chip. Such multiprocessor systems are termed multi-cores. They can be more efficient than multiple chips with single cores, as on-chip communication is faster than between-chip communication. In addition, one chip with multiple cores uses significantly less power than multiple single core chips. It's important to note that while multi core systems are multiprocessor systems, not all multiprocessor systems are multi core. In our coverage of multiprocessor systems throughout this text, unless we state otherwise, we generally use the more contemporary term, which is multi core, which excludes some multiprocessor systems. In this figure 1.7, a dual core design with two cores placed on the same chip with, with a shared memory, as shown in this picture, which consists of two cores, CPU core 0 and CPU core 1. In CPU core 0, there are the registers and the cache, and also in the core 1, there are its own registers and its own cache. In the previous figure, we show a dual core design with two cores on the same chip. In the design, each core has its own register set as well as its own local cache. Other designs might use a shared cache or a combination of local and shared caches. Aside from architecture considerations such as cache, memory, and bus contention, these multi-core CPUs appear to the operating system as in standard processors. This characteristic puts pressure on operating system designers and application programs to make use of those processing cores. Finally, blade servers are relatively recent development in which multiple processor ports, input-out ports, and network ports are placed in the same chassis. The difference between these are traditional multiprocessor systems is that each blade server port puts independently and run its own operating system. Some blade server ports are multiprocessor as well, which blurs the lines between types of computers. In essence, these servers consist of multiple independent multiprocessor systems. Third one, the clustered systems. Another type of multiprocessor system is the clustered system, which gather together multiple CPUs. Clustered systems differ from the multiprocessor systems described before in that they are composed of two or more individual systems or nodes joined together. Such systems are considered loosely coupled. Each node may be a single processor system or a multi-core system. We should note that the definition of clustered is not concrete. Many commercial packages wrestle to define a clustered system and why one form is better than another. The generally accepted definition is that clustered computers share storage and are closely linked via a local area network or LAN, or a faster interconnect such as InfiniBand. Clustering is usually used to provide high availability service. That the service will continue even if one or more systems in the cluster fail. Generally, we obtain high availability by adding a level of redundancy in the system. A layer of cluster software runs on the cluster nodes. Each node can monitor one or more of the others over the LAN. If the monitored machine fails, the monitoring machine can take ownership of its storage and restart the applications that were running on the failed machine. The users and clients of applications see only a brief of interruption of service. Clustering can be structured asymmetrically or symmetrically. In asymmetric clustering, one machine is in hot standby mode, while the other is running the applications. The hot standby host machine does nothing but monitor the active server. If that server fails, the hot standby host becomes the active server. In symmetric clustering, two or more hosts are running applications and are monitoring each other. This structure is obviously more efficient as it uses all of the available hardware. However, it does require that more than one application be available to run. Since a cluster consists of several computer systems connected via a network, clusters can also be used to provide a high performance computing environments. Such systems can supply significantly greater computational power than a single processor or even SMP systems because they can run an application concurrently on all computers in the cluster. The application must have been written specifically to take advantage of the cluster. This involves a technique known as parallelization, which divides a program into separate components that run in parallel on individual computers in the cluster. Typically, these applications are designed so that once each computing node in the cluster has solved its portion of the problem, the results from all the nodes are combined into a final solution. Other forms of clusters include parallel clusters and clustering over a wide area network or WAN. Parallel clusters allow multiple hosts to access the same data on a shared storage. Because most operating systems lack support for simultaneous data access by multiple hosts, parallel clusters usually require the use of special versions of software and special releases of applications. For example, Oracle Real Application Cluster is a version of Oracle's database that has been designed to run on a parallel cluster. Each machine runs Oracle, and a layer of software tracks access to the shared disk. Each machine has full access to all data in the database. To provide this shared access, the system must also supply access control and locking to ensure that no conflicting operations occur. This function commonly known as a distributed lock manager or DLM, which is included in some cluster technology. Cluster technology is changing rapidly. Some cluster products support dozens of systems in a cluster, as well as clustered nodes that are separated by miles. Many of these improvements are made possible by storage area networks or SANs, which allow many systems to attach to a pool of storage. If the applications and their data are stored on the SAN, then the cluster software can assign the application to run on any host that is attached to the SAN. If the host fails, then any other host can take over. In a database cluster, dozens of hosts can share the same database, greatly increasing performance and reliability. The next figure depicts the general structure of a clustered system. Figure 1.8 General structure of a clustered system, which consists from computer with an interconnection with another computer and interconnection with other computers. And all these computers is connected with a SAN storage or storage area network. Now that we have discussed the basic computer system organization and architecture, we are ready to talk about operating systems. The operating system structure. An operating system provides the environment within which the programs are executed. Internally, operating systems vary greatly in their makeup since they are organized along many different lines. There are, however, many commonalities which we consider in this section. One of the most important aspects of operating system is the ability to multi-program. A single program cannot in general keep either the CPU or the input-output devices busy at all times. Single users frequently have multiple programs running. Multi-programming increases CPU utilization by organizing jobs, code, and data, so that the CPU always has one program to execute. Figure 1.9 Memory layout for a multi-programming system. The memory consists of operating system and job 1, job 2, job 3, job 4, from 0 to max of the memory. The idea is as follows. The operating system keeps several jobs in memory simultaneously, as shown in the previous picture. Since in general main memory is too small to accommodate all jobs, the jobs are kept initially on the disk in the job pool. This pool consists of all processes residing on disk awaiting allocation of main memory. The set of jobs in memory can be a subset of the jobs kept in the job pool. The operating system picks and begins to execute one of the jobs in memory. Eventually, the job may have to wait for some task, such as input-output operation, to complete. In a non-multi-programmed system, the CPU will sit idle. In a multi-programmed system, the operating system simply switches to and executes another job. When that job needs to wait, the CPU switches to another job and so on. Eventually, the first job finishes waiting and gets the CPU back. As long as at least one job needs to execute, the CPU is never idle. This idea is common in other life situations. A lawyer doesn't work for only one client at a time. For example, while one case is waiting to go to trial or have papers typed, the lawyer can work on another case. If he has enough clients, the lawyer will never be idle for lack of work. Idle lawyers tend to become politicians. So there is a certain social value in keeping lawyers busy. Multi-programmed systems provide an environment in which the various system resources, for example CPU, memory, and peripheral devices, are utilized effectively but they do not provide for user interaction with the computer system. Time sharing or multitasking is a logical extension of multi-programming. In time sharing systems, the CPU executes multiple jobs by switching among them, but the switches occur so frequently that the users can interact with each program while it's running. Time sharing requires an interactive computer system, which provides direct communication between the user and the system. The user gives instructions to the operating system or to program directly, using an input device such as a keyboard, mouse, touchpad, or touch screen, and waits for immediate results on an output device. Accordingly, the response time should be short, typically less than 1 second. A time-shared operating system allows many users to share the computer simultaneously. Since each action or command in a time-shared system tends to be short, only a little CPU time is needed for each user. As the system switches rapidly from one user to the next, each user is given the impression that the entire computer system is dedicated to his use, even though it's being shared among users. A time-shared operating system used CPU scheduling and multi-programming to provide each user with a small portion of a time-shared computer. Each user has at least one separate program in memory. A program loaded into memory and executing is called a process. When a process executes, it typically executes for only a short time before it either finishes or needs to perform input-output. Input-output may be interactive. That's output goes to a display for the user, and the input comes from a user keyboard, mouse, or other device. Since the interactive input-output typically runs at people speeds, it may take a long time to complete. Input, for example, may be bounded by the user's typing speed. 7 characters per second is fast for people, but incredibly slow for computers. Rather than let the CPU sit idle as this interactive input takes place, the operating system will rapidly switch the CPU to the program of some other user. Time sharing and multi-programming require that several jobs be kept simultaneously in memory. If several jobs are ready to be brought into memory, and if there is not enough room for all of them, then the system must choose among them. Making this decision involves job scheduling. When the operating system selects a job from the job pool, it loads that job into memory for execution. Having several programs in memory at the same time requires some form of memory management. In addition, if several jobs are ready to run at the same time, the system must choose which job will run first. Making this decision is a CPU scheduling. Finally, running multiple jobs concurrently requires that their ability to affect one another be limited in all phases of the operating system, including process scheduling, disk storage, and the memory management. In a time sharing system, the operating system must ensure reasonable response time. This goal is sometimes accomplished through swapping, whereby processes are swapped in and out of main memory to the disk. A more common method for ensuring reasonable response time is virtual memory, which is a technique that allows the execution of a process that is not completely in memory. The main advantage of the virtual memory scheme is that it enables users to run programs that are larger than the actual physical memory. Further, it abstracts main memory into a large uniform array of storage, separating logical memory as viewed by the user from physical memory. This arrangement frees programs from concern over memory storage limitations. A time-sharing system must also provide a file system. The file system resides on a collection of disks. Hence, disk management must be provided. In addition, a time-sharing system provides a mechanism for protecting resources from inappropriate use. To ensure orderly execution, the system must provide mechanisms for job synchronization and communication, and it may ensure that jobs do not get stuck in a deadlock forever, waiting for one another. As mentioned earlier, modern operating systems are interrupt driven. Now, with the operating system operations, if there are no processes to execute, no input output devices to service, and no users to whom to respond, and operating system will sit quietly, waiting for something to happen. Events are almost always signaled by the occurrence of an interrupt or a trap. A trap or an exception is a software generated interrupt caused either by an error, for example, division by zero, or invalid memory access, or by a specific request from a user program that an operating system service be performed. The interrupt driven nature of an operating system defines that system's general structure. For each type of interrupt, separate segments of code in the operating system determine what action should be taken. An interrupt service routine is provided to deal with the interrupt. Since the operating system and the users share the hardware and software resources of the computer system, we need to make sure that an error in a user program could cause problems only for the only for the one program running. With sharing many processes could be adversely affected by a bug in one program. For example, if a process gets stuck in an infinite loop, this loop could prevent the correct operation of many other processes. More subtle errors can occur in a multi-programming system, where one erroneous program might modify another program, the data of another program, or even the operating system itself. Without protection against these sorts of errors, either the computer must execute only one process at a time or all output must be suspect. A properly designed operating system must ensure that an incorrect or malicious program cannot cause other programs to execute incorrectly. First, dual mode and multi-mode operation. In order to ensure the proper execution of the operating system, we must be able to distinguish between the execution of operating system code and the user-defined code. The approach taken by most computer systems is to provide hardware support that allows us to differentiate among various modes of executions. In Figure 1.10, transition from user to kernel mode. There is a user mode and a kernel mode, where the user process executing calls a system call, which make a trap and mode bit equal 0, and go down to the kernel mode to execute the system call. After that, it return and the mode bit equal 1, and then return from system call in the user mode, which mode bit equal 1. And so there are two important modes, user mode and kernel mode. At the very least, we need two separate modes of operation, user mode and kernel mode, also called supervisor mode or system mode or privileged mode. A bit called the mode bit is added to the hardware of the computer to indicate the current mode, kernel 0 or the user mode 1. With the mode bit, we can distinguish between a task that is executed on behalf of the operating system and one that executed on behalf of the user. When the computer system is executing on behalf of a user application, the system is in the user mode. However, when a user application requests a service from the operating system via a system call, the system must transition from the user mode to the kernel mode to fulfill this request. This is shown in the previous figure 1.10. As we shall see in the figure, this architecture enhancement is useful for many other aspects of system operation as well. At system boot time, the hardware starts in kernel mode. The operating system is then loaded and starts user applications in user mode. Whenever a trap or interrupt occurs, the hardware switches from user mode to kernel mode. That changes the state of the mode bit to 0. Thus, whenever the operating system gains control of the computer, it's in the kernel mode. The system always switches to user mode by setting the mode bit to 1 before passing control to a user mode. The dual mode of operation provides us with the means for protecting the operating system from errant users and errant users from one another. We accomplish this protection by designating some of the machine instructions that may cause harm as privileged instructions. The hardware allows privileged instructions to be executed only in the kernel mode. If an attempt is made to execute privileged instruction in user mode, the hardware doesn't execute the instruction, but rather treats it as illegal and traps it to the operating system. The instruction to switch to the kernel mode is an example of a privileged instruction. Some other examples include input-output control, timer management, and interrupt management. As we shall see throughout this lesson, there are many additional privileged instructions. The concept of modes can be extended beyond 2 modes, in which case the CPU uses more than one bit to set and test the mode. CPUs that support virtualization frequently have a separate mode to indicate when the Virtual Machine Manager or VMM and the virtualization management software is in control of the system. In this mode, the VMM has more privileges than user processes, but fewer than the kernel. It needs that level of privilege so it can create and manage virtual machines, changing the CPU state to do so. Sometimes 2 different modes are used by various kernel components. We should note that, as an alternative to modes, the CPU designer may use other methods to differentiate operational privileges. The Intel 64 family of CPUs supports 4 privilege levels, for example, and supports virtualization but doesn't have a separate mode for virtualization at CPU. We can now see the life cycle of instruction execution in a computer system. Initial control resides in the operating system where instructions are executed in the kernel mode. When control is given to a user application, the mode is set to user mode. Eventually, control is switched back to the operating system via an interrupt or a trap or a system call. System calls provide the means for a user program to ask the operating system to perform tasks reserved for the operating system on the user program's behalf. A system call is invoked in a variety of ways, depending on the functionality provided by the underlying processor. In all forums, it's the method used by a process to request action by the operating system. A system call usually takes the form of a trap to a specific location in the interrupt vector. This trap can be executed by a generic trap instruction, also sometimes such as MIPS, which have a specific syscall instruction to invoke a system call. When a system call is executed, it's typically treated by the hardware as a software interrupt. Control passes through the interrupt vector to a service routine in the operating system, and the mode bit is set to the kernel mode. The system call service routine is a part of the operating system. The kernel examines the interrupting instruction to determine what system call has occurred. A parameter indicates what type of service the user program is requesting. Additional information needed for the request may be passed in registers, on the stack, or in the memory, with pointers to the memory locations passed in registers. The kernel verifies that the parameters are correct and legal, executes the request, and returns control to the instruction following the system call. The lack of a hardware supported dual mode can cause serious shortcomings in an operating system. For instance, Microsoft DOS was written for the Intel 8088 architecture, which has no mode bit and therefore no dual mode. A user program running array can wipe out the operating system by writing over it with data, and multiple programs are able to write to a device at the same time, with potentially disastrous results. Modern versions of the Intel CPU do provide dual mode operation. Accordingly, most contemporary operating systems, such as Microsoft Windows 7, as well as Unix and Linux, take advantage of this dual mode feature and provide greater protection for the operating system. Once hardware protection is in place, it detects errors that violate modes. These errors are normally handled by the operating system. If a user program fails in some way, such as by making an attempt either to execute an illegal instruction or to access memory that's not in the user's address space, then the hardware traps to the operating system. The trap transfers control through the interrupt vector to the operating system, just as an interrupt does. When a program error occurs, the operating system must terminate the program abnormally. This situation is handled by the same code as a user requested abnormal termination. An appropriate error message is given, and the memory of the program may be dumped. The memory dump is usually written to a file so that the user or programmer can examine it and perhaps correct it and restart the program. Second, the timer. We must ensure that the operating system maintains control over the CPU. We cannot allow a user program to get stuck in an infinite loop or to fail to call system services and never return control to the operating system. To accomplish this goal, we can use a timer. A timer can be set to interrupt the computer after a specified period. The period may be fixed, for example, 1 from 16 seconds, or variable, from example, from 1 millisecond to 1 second. A variable timer is generally implemented by a fixed rate clock and a counter. The operating system sets the counter. Every time the clock ticks, the counter is decremented. When the counter reaches zero, an interrupt occurs. For instance, a 10-bit counter with a 1 millisecond clock allows interrupts at intervals from 1 millisecond to 124 milliseconds in steps of 1 millisecond. Before turning over control to the user, the operating system ensures that the timer is set to interrupt. If the timer interrupts, control transfers automatically to the operating system, which may treat the interrupt as a fatal error, or may give the program more time. Clearly, instructions that modify the content of the timer are privileged. We can use the timer to prevent a user program from running too long. A simple technique is to initialize a counter with the amount of time that a program is allowed to run. A program with a 7-minute time limit, for example, would have its counter initialized to 420. Every second the timer interrupts and the counter is decremented by 1. As long as the counter is positive, control is returned to the user program. When the counter becomes negative, the operating system terminates the program for exceeding the assigned time limit. Now with the process management. A program does nothing unless its instructions are executed by a CPU. A program in execution is mentioned is a process. A time-shared user program such as a compiler is a process. A word processing program being run by an individual user on a PC is a process. A system stack such as sending output to a printer can also be a process, or at least part of one. For now, you can consider a process to be a job or a time-shared program, but later you will learn that the concept is more general. It's possible to provide system calls that allow processes to create sub-processes to execute concurrently. A process needs certain resources, including CPU time, memory, files, and input-output devices to accomplish its task. These resources are either given to the process when it's created or allocated to it while it's running. In addition to the various physical and logical resources that a process obtains when it's created, various initialization data input may be passed along. For example, consider a process whose function is to display the status of a file on the screen of a terminal. The process will be given the name of the file as an input and will execute the appropriate instructions and system calls to obtain and display the desired information on the terminal. When the process terminates, the operating system will reclaim any reusable resources. We emphasize that a program by itself is not a process. A program is a passive entity, like the contents of a file stored on a disk, whereas a process is an active entity. A single threaded process has one program counter specifying the next instruction to execute. Threads are covered next in part 4. The execution of such a process must be sequential. The CPU executes one instruction of the process after another until the process completes. Further, at any time, one instruction at most is executed on behalf of the process. Thus, although two processes may be associated with the same program, they are nevertheless considered two separate execution sequences. A multi-threaded process has multiple program counters, each pointing to the next instruction to execute for a given thread. A process is the unit of work in a system. A system consists of collection of processes, some of which are operating system processes, those that execute system code, and the rest of which are user processes, those that execute the user code. All these processes can potentially execute concurrently by multiplexing on a single CPU. For example, the operating system is responsible for the following activities in connection with process management: scheduling processes and threads on the CPUs, creating and deleting both user and system processes, suspending and resuming processes, providing mechanisms for process synchronization, providing mechanisms for process communication. And we will discuss process management techniques next in part 3. Now with the memory management. As we discussed before, the main memory is central to the operation of a modern computer system. Main memory is a large array of bytes, ranging in size from hundreds of thousands to billions. Each byte has its own address. Main memory is a repository of quickly accessible data shared by the CPU and by the input-output devices. The central process reads instructions from main memory during the instruction fetch cycle, and both reads and writes data from main memory during the data fetch cycle on a von Neumann architecture. As noted earlier, the main memory is generally the only large storage device that the CPU is able to address and access directly. For example, for the CPU to process data from disk, those data must first be transferred to the main memory by CPU-generated input-output calls. In the same way, instructions must be in memory for the CPU to execute them. For a program to be executed, it must be mapped to absolute addresses and loaded into memory. As a program executes, it accesses programs instructions and data from memory by generating these absolute addresses. Eventually, the program terminates, its memory space is declared available, and the next program can be loaded and executed. To improve both the utilization of the CPU and the speed of the computer's response to its users, general purpose computers must keep several programs in memory, creating a need for memory management. Many different memory management schemes are used. These schemes reflect various approaches, and the effectiveness of any given algorithm depends on the situation. In selecting a memory management scheme for a specific system, we must take into account many factors, especially the hardware design of the system. Each algorithm requires its own hardware support. The operating system is responsible for the following activities in connection with memory management: keeping track of which parts of memory are currently being used and who is using them, deciding which processes or parts of processes and data to move into and out of memory, allocating and deallocating memory space as needed. Memory management techniques are discussed next in Part 8 and Part 9. Now, with the storage management. To make the computer system convenient for users, the operating system provides a uniform logical view of information storage. The operating system abstracts from the physical properties of its storage devices to define a logical storage unit, the file. The operating system maps files onto physical media and accesses these files via the storage devices. First, the file system management. File management is one of the most visible components of an operating system. Computers can store information on several different types of physical media. Magnetic disk, optical disk, and magnetic tape are the most common. Each of these media has its own characteristics and physical organization. Each medium is controlled by a device, such as a disk drive or tape drive, that also has its own unique characteristics. These properties include access speed, capacity, data transfer rate, and access method, sequential or random. A file is a collection of related information, which is defined by its creator. Commonly, files represent programs, both source and object forms, and data. Data files may be numeric, alphabetic, alphanumeric, or binary. Files may be free form, for example, text files, or they may be formatted rigidly, For example, fixed fields. Clearly, the concept of a file is an extremely general one. The operating system implements the abstract concept of a file by managing mass storage media, such as tabs and disks, and the devices that control them. In addition, files are normally organized into directories to make them easier to use. Finally, when multiple users have access to files, it may be desirable to control which user may access a file and how that user may access it. For example, read, write, and append privileges. The operating system is responsible for the following activities in connection with the file management: creating and deleting files, creating and deleting directories to organize files, supporting primitives for manipulating files and directories, mapping files onto secondary storage, backing up files on stable, non-volatile storage media. File management techniques will be discussed in parts 11 and parts 12. Now with the second, mass storage management. As we have already seen, because main memory is too small to accommodate all data and programs, and because the data that it holds are lost when power is lost, the computer system must provide secondary storage to back up main memory. Most modern computer systems use disks as the principal online storage medium for both programs and data. Most programs, including compilers, assemblers, word processors, editors, and formatters, are stored on a disk until loaded into memory. Then, they use the disk as both the source and destination of their processing. Hence, the proper management of disk storage is of central importance to a computer system. The operating system is responsible for the following activities on connection with disk management: free space management, storage allocation, disk scheduling. Because secondary storage is used frequently, it must be used efficiently. The entire speed of operation of a computer may hang on the speeds of the disk subsystem and the algorithms that manipulate that subsystem. There are, however, many uses of storage for storage that is slower and lower in cost, and sometimes of higher capacity than secondary storage. Backups of disk data, storage of seldom used data, and long term archival storage are some examples. Magnetic tape drives and their tabs and CD and DVD drives and platters are typical tertiary storage devices. The media tabs and optical platters vary between WORM, or write once, read many times, and RW, which is read and write formats. Tertiary storage is not crucial to system performance, but it still must be managed. Some operating systems take on this task while others leave tertiary storage management to application programs. Some of the functions that the operating systems can provide include mounting and unmounting media in devices, allocating and freeing the devices for exclusive use by processes, and migrating data from secondary to tertiary storage. Techniques for secondary and tertiary storage management are discussed in Part 10. Third, caching. The caching is an important principle of computer systems. Here's how it works. Information is normally kept in some storage system such as main memory. As it's used, it's copied into a faster storage system, the cache, on a temporary basis. When we need a particular piece of information, we first check whether it's in the cache. If it is, we use the information directly from the cache. If it is not, we use the information from the source, putting a copy in the cache under the assumption that we will need it again soon. In addition, internal programmable registers such as index registers provide a high-speed cache for main memory. The programmer or compiler implements the register allocation and register replacement algorithms to decide which information to keep in registers and which to keep in main memory. Other caches are implemented totally in hardware. For instance, most systems have an instruction cache to hold the instructions expected to be executed next. Without this cache, the CPU would have to wait several cycles while an instruction was fetched from the main memory. For similar reasons, most systems have one or more high-speed data caches in the memory hierarchy. We are not concerned with these hardware-only caches in this text, since they are outside the control of the operating system. Because caches have limited size, cache management is an important design problem. Careful selection of the cache size and of a replacement policy can result in greatly increased performance. The next figure 1.11 compares storage performance in large workstations and small servers. Various replacement algorithms for software-controlled caches are discussed in Part 9. The figure 1.11 performance of various levels of storage. We have the level 1 and 2 and 3 and 4 and 5. The name of level 1 is the registers, and 2 caches, and 3 main memory, and 4 the solid state disks, and 5 magnetic disks. The typical size for registers is less than 1 kilobyte, and for 2 caches is less than 16 megabyte, and for main memory is less than 64 gigabyte, and for solid state disks is less than 1 terabyte, and for magnetic disks less than 10 terabytes. The implementation technology for registers is the custom memory with multiple ports or CMOS. For cache is on-chip or off-chip CMOS SRAM or static RAM. And the implementation technology for main memory is CMOS SRAM or static RAM. And for the solid state disk, the technology is the flash memory. And for magnetic disk, the technology is the magnetic disk. The access time in nanosecond for registers is 0.25 to 0.5 nanosecond, and the access time for cache is 0.5 to 25 nanosecond, and for main memory is 80 to 250 nanosecond, and is for the solid state disk is 25,000 to 55,000 nanosecond, and for the magnetic disk the access time is 5 million nanosecond. The bandwidth or the size of data that being transferred in megabytes per second, which in registers 20,000 to 100,000 megabyte per second, and in caches 5,000 to 10,000 megabyte per second, and in main memory 1,000 to 5,000 megabyte per second, and for the solid state disk 500 megabyte per second, and for the magnetic disk 20 to 150 megabyte per second as a bandwidth. The registers is managed by the compiler, and the caches is managed by the hardware. The main memory is managed by the operating system. The solid state disk and the magnetic disk also are managed by the operating system. The registers are backed up by the caches. and the caches are up by the main memory. The main memory packed by the disk. The solid state disk packed also by the disk. And the magnetic disk is backed up by the disk or by tabs. We still with the storage management. Main memory can be viewed as a fast cache for secondary storage, since data in secondary storage must be copied into main memory for use and data must be in main memory before being moved to secondary storage for safekeeping. The file system data which resides permanently on secondary storage may appear on several levels in the storage hierarchy. At the highest level, the operating system may maintain a cache of file system data in main memory. In addition, solid-state disks may be used for high-speed storage that is accessed through the file system interface. The bulk of secondary storage is on magnetic disks. The magnetic disk's storage in turn is often packed up onto a magnetic tabs or removable disks to protect against data loss in case of a hard disk failure. Sometimes automatically archive all the file data from secondary storage to tertiary storage, such as tab jacks, jack boxes, to lower the storage cost, which in part 10. The movement of information between levels of a storage hierarchy may be either explicit or implicit, depending on the hardware design and the controlling operating system software. For instance, data transfer from cache to CPU and registers is usually a hardware function with no operating system intervention. In contrast, transfer of data from disk to memory is usually controlled by the operating system. In a hierarchical storage structure, the same data may appear in different levels of the storage system. For example, suppose that an integer a that is to be incremented by 1 is located in file P and the file P resides on a magnetic disk. The increment operation proceeds by first issuing an input-output operation to copy the disk block on which A resides to main memory. This operation is followed by copying A to the cache and to an internal register. Thus, the copy of A appears in several places on the magnetic disk, in main memory and in the cache, and in an internal register, as shown in the figure 1.12. Figure 1.12, migration of integer A from disk to register. The integer A is located on magnetic disk, also in the main memory, also in the cache, and after that is in the hardware register. Once the increment takes place in the internal register, the value of A differs in the various storage systems. The value of A becomes the same only after the new value of A is written from the internal register back to the magnetic disk. In a computing environment where only one process executes at a time, this arrangement poses no difficulties, since an access to integer A will always be to the copy at the highest level of the hierarchy. However, in a multitasking environment, where the CPU is switched back and forth among various processes, extreme care must be taken to ensure that if several processes wish to access A, then each of these processes will obtain the most recently updated value of A. The situation becomes more complicated in a multiprocessor environment, where in addition to maintaining internal registers, each of the CPUs also contains a local cache, as shown preceded in figure 1.6. In such an environment, a copy of A may exist simultaneously in several caches. Since the various CPUs can all execute in parallel, We must make sure that an update to the value of A in one cache is immediately reflected in all other caches where A resides. This situation is called cache coherency, and it's usually a hardware issue handled below the operating system level. In a distributed environment, the situation becomes even more complex. In this environment, several copies of replicas of the same file can be kept on a different computers. Since the various replicas may be accessed and updated concurrently, some distributed systems ensure that when a replica is updated in one place, all other replicas are brought up to date as soon as possible. There are various ways to achieve this guarantee, as we discuss in part 17. Fourth, the input-output systems. One of the purposes of an operating system is to hide the peculiarities of specific hardware devices from the user. For example, in Unix, the peculiarities of the input-output devices are hidden from the bulk of the operating system itself by the input-output subsystem. The input-output subsystem consists of several components. A memory management component that includes buffering, caching, and spooling, also a general device driver interface, and a drivers for specific hardware devices. Only the device driver knows the peculiarities of the specific device to which it's assigned. We discussed in previous how interrupt handlers and device drivers are used in the construction of efficient input-output subsystems. In part 13, we discuss how the input-output subsystem interfaces to the other system components, manages devices, transfers data, and detects the input-output completion. Now with the protection and security. If a computer system has multiple users and allows the concurrent execution of multiple processes, then access to data must be regulated. For that purpose, mechanisms ensure that files, memory, segments, CPU, and other resources can be operated on by only those processes that have gained proper authorization from the operating system. For example, memory addressing hardware ensures that a process can execute only within its own address space. The timer ensures that no process can gain control of the CPU without eventually relinquishing, relinquishing control. Device control registers are not accessible to users, so the integrity of the various peripheral devices is protected. Protection then is any mechanism for controlling the access of processes or users to the resources defined by a computer system. This mechanism must provide means to specify the controls to be imposed and to enforce the controls. Protection can improve reliability by detecting latent errors at the interfaces between component subsystems. Early detection of interface errors can often prevent contamination of a healthy subsystem by another subsystem that is malfunctioning. Furthermore, an unprotected resource cannot defend against use or misuse by an unauthorized or incompetent user. A protection oriented system provides a means to distinguish between authorized and unauthorized usage, as we discussed in part 14. A system can have adequate protection but still be prone to failure and allow inappropriate access. Consider a user whose authentication information, her means of identifying herself to the system, is stolen. Her data could be copied or deleted even though file and memory protection are working. It's the job of security to defend a system from external and internal attacks. Such attacks spread across a huge range and include viruses and worms, denial of service attacks, which use all of the system's resources and so keep legitimate users out of the system, ident- identity theft and theft of service, unauthorized use of a system. Prevention of some these attacks is considered an operating system function on some systems, while other systems leave it to policy or additional software. Due to the alarming rise in security incidents, operating system security features represent a fast growing area of research and implementation. We will discuss security in part 15, inshallah. Protection and security requires the system to be able to distinguish among all its users. Most operating systems maintain a list of user names and associated user identifiers or user IDs. In Windows parlance, this is a security ID or SID. These numerical IDs are unique, one per user. When a user logs into the system, the authentication stage determines the appropriate user ID for the user. That user ID is associated with all of the user's processes and threats. When an ID needs to be readable by a user, it's translated back to the username via the username list. In some circumstances, we wish to distinguish among sets of users rather than individual users. For example, the owner of a file on a Unix system to may be allowed to issue all operations on that file, whereas a selected set of users may be allowed only to read the file. To accomplish this, we need to define a group name and the set of users belonging to that group. Group functionality can be implemented as a system-wide list of group names and group identifiers. A user can be in one or more groups depending on operating system design decisions. The user's group IDs are also included in every associated process and thread. In the course of normal system use, the user ID and group ID for a user are sufficient. However, a user sometimes needs to escalate privileges to gain extra permissions for an activity. The user may need access to a device that is restricted. For example, operating systems provide various methods to allow privilege escalation. On a Unix, for instance, the setUID attribute on a program causes that program to run with the user ID of the owner of the file, rather than the current user's ID. The process runs with this effective UID until it turns off the extra privileges or terminates. Now with the kernel data structures. We turn next to a topic central to operating system implementation, the way data are structured in the system. In this section, we briefly describe several fundamental data structures used extensively in operating systems. Readers who require further details on these structures as well as others should consult the bibliography at the end of the chapter. Now, first, with the lists, stacks, and queues. An array is a simple data structure in which each element can be accessed directly. For example, main memory is constructed as an array. If the data item being stored in larger than 1 byte, then multiple bytes can be allocated to the item, and the item is addressed as item number x item size. But what about storing an item whose size may vary? And what about removing an item if the relative positions of the remaining items must be preserved? In such situations, arrays give way to other data structures. After arrays, lists are perhaps the most fundamental data structures in computer science. whereas each item in an array can be accessed directly. The items in a list must be accessed in a particular order. That's a list represents a collection of data values as a sequence. The most common method for implementing this structure is a linked list in which items are linked to one another. Linked lists are of several types. In a singly linked list, each item points to its successor, as illustrated in the next figure 1.13. In the second type, a doubly linked list, a given item can refer either to its predecessor or to its successor, as illustrated in figure 1.14. In a circularly linked list, the last element in the list refers to the first element, rather than to null, as illustrated in figure 1.15. Those are the three previous figures which we've mentioned. First, the figure 1.13, it's for the singly linked list. And second, the figure 1.14, it's for the doubly linked list. And lastly, figure 1.15, it's for the circularly linked list. Linked lists accommodate items of varying sizes and allow easy insertion and deletion of items. One potential disadvantage of using a list is that performance for retrieving a specified item in a list of size n is linear. ON, as it requires potentially traversing all n elements in the worst case. Lists are sometimes used directly by kernel algorithms. Frequently, through they are used for constructing more powerful data structures, such as stacks and queues. A stack is a sequentially ordered data structure that uses the last in first out or LIFO principle for adding and removing items, meaning that the last item placed onto a stack is the first item removed. The operations for inserting and removing items from a stack are known as push and pop, respectively. An operating system often uses a stack when invoking function calls. Parameters, local variables, and the return address are pushed onto the stack when a function is called. Returning from the function call pops those items of the stack. A queue, in contrast, is a sequentially ordered data structure that uses the first in, first out, or FIFO principle. Items are removed from a queue in the order in which they were inserted. There are many everyday examples of queues, including shoppers waiting in a checkout line at a store, and cars waiting in a line at a traffic signal. Queues are also quite common in operating systems. Jobs that are sent to a printer are typically printed in the order in which they were submitted. For example, as we shall see in part 6, tasks that are waiting to be run on an available CPU are often organized in queues. Second, the trees. A tree is a data structure that can be used to represent data hierarchically. Data values in a tree structures are linked through parent-child relationships. In a general tree, a parent may have an unlimited number of children. In a binary tree, a parent may have at most two children, which we term the left child and the right child. A binary search tree additionally requires an ordering between the parent's two children, in which left child must be less than or equal the right child. The next figure 1.16 provides an example of a binary search tree. When we search for an item in a binary search tree, the worst case performance is ON. Consider how this can occur. To remedy this situation, we can use an algorithm to create a balanced binary search tree. Here, a tree containing n items has at most LGN levels, thus ensuring worst-case performance of all LGN. We shall see in section 6.7.1 that Linux uses a balanced binary search tree as part its CPU scheduling algorithm. This figure 1.16 is for the binary search tree, and the figure below, figure 1.17, is for the hash map data structures, which we will take next. Third, the hash functions and maps. A hash function takes data as its input, performs a numeric operation on this data, and returns a numeric value. This numeric value can then be used as an index into a table, typically an array, to quickly retrieve the data. Whereas searching for a data item through a list of size n can require up to ON comparisons in the worst case. Using the hash function for retrieving data from table can be as good as O1 in the worst case, depending on implementation details. Because of this performance, hash functions are used extensively in operating systems. One potential difficulty with hash functions is that two inputs can result in the same output value, that they can link to the same table location. We can accommodate this hash collision by having a linked list at that table location that contains all of the items with the same hash value. Of course, the more collisions there are, the less efficient the hash function is. On use of a hash function is to implement a hash map, which associates or maps key value pairs using a hash function. For example, we can map the key operating to the value system. Once the mapping is established, we can apply the hash function to the key to obtain the value from the hash map, which is in the previous figure 1.17. For example, suppose that a username is mapped to a password. Password authentication then proceeds as follows. A user enters his username and password. The hash function is applied to the username, which is then used to retrieve the password. The retrieved password is then compared with the password entered by the user for authentication. Fourth, the bitmaps. A bitmap is a string of n binary digits that can be used to represent the status of n items. For example, suppose we have several resources and the availability of each resource is indicated by the value of binary digit 0. 0 means that the resource is available, while 1 indicates that it's unavailable, or vice versa. The value of the ith position in the bitmap is associated with the ith resource. As an example, consider the bitmap showing 00101101. Resources 2, 4, 5, 6, and 8 are unavailable. Resources 0, 1, 3, and 7 are available. The power of bitmaps becomes apparent when we consider their space efficiency. If we were to use an 8-bit Boolean value instead of a single bit, the resulting data structures would be 8 times larger. Thus, bitmaps are commonly used when there is a need to represent the availability of a large number of resources. Disk drives provide a nice illustration for that. A medium-sized disk drive might be divided into several thousand individual units, called disk blocks. A bitmap can be used to indicate the availability of each disk block. Data structures are pervasive in operating system implementations. Thus, We will see the structures discussed here along with others throughout this text as we explore kernel algorithms and their implementations. And this picture is showing some information about the Linux kernel data structures. Now with the computing environments. So far, we have briefly described several aspects of computer systems and the operating systems that manage them. We turn now to a discussion of how operating systems are used in a variety of computing environments. First, the traditional computing. As computing has matured, the lines separating many of the traditional computing environments have blurred. Consider the typical office environment. Just a few years ago, this environment consisted of a PCs connected to a network, with servers providing file and print services. Remote access was awkward, and portability was achieved by use of laptops computers. Terminals attached to mainframes were prevalent at many companies as well. With even fewer remote access and portability options, the current trend is toward providing more ways to access these computing environments. Web technologies and increasing WAN bandwidth are stretching the boundaries of traditional computing. Companies establish portals which provide web accessibility to their internal servers. Network computers or thin clients, which are essentially terminals that understand web based computing, are used in place of traditional workstations where more security or easier maintenance is desired. Mobile computers can synchronize with PCs to allow very portable use of company information. Mobile computers can also connect to wireless networks and cellular data networks to use the company's web portal as well as a myriad other web resources. At home, most users once had a single computer with a slow modem connection to the office, the internet, or both. Today, network connection speeds, once available only at great cost, are relatively inexpensive in many places, giving home users more access to more data. These fast data connections are allowing home computers to serve up web pages and to run networks that include printers, client PCs, and servers. Many homes use firewalls to protect their network from security breaches. In the later half of the 20th century, computing resources were relatively scarce. Before that, they were non existent. For a period of time, systems were either batch or interactive. Batch systems processed jobs in bulk with predetermined input from files or other data sources. Interactive systems waited for input from users. To optimize the use of the computing resources, multiple users shared the time on these systems. Time sharing systems used a timer and scheduling algorithms to cycle processes rapidly through the CPU, giving each user a share of the resources. Today, traditional time sharing systems are uncommon. The same scheduling technique is still in use on desktop computers, laptops, servers, and even mobile computers, but frequently all the processes are owned by the same user or a single user and the operating system. User processes and system processes that provide services to the user are managed so that each frequently gets a slice of computer time. Consider the windows created while a user is working on a PC, for example, and the fact that they may be performing different tasks at the same time. Even a web browser can be composed of multiple processes, one for each website currently being visited, with time sharing applied to each web browser process. Now, second, The mobile computing. Mobile computing refers to computing on handheld smartphones and tablet computers. These devices share the distinguishing physical features of being portable and lightweight. Historically, compared with desktop and laptop computers, mobile systems gave up screen size, memory capacity, and overall functionality in return for handheld mobile access to services such as email and web browsing. Over the past few years, however, features on mobile devices have become so rich that the distinction in functionality between, say, a consumer laptop and a tablet computer may be difficult to discern. In fact, we might argue that the features of a contemporary mobile device allow it to provide functionality that's either unavailable or impractical on a desktop or laptop computer. Today, mobile systems are used not only for email and web browsing, but also for playing music and video, reading digital books, taking photos, and recording high definition video. Accordingly, tremendous growth continues in the wide range of applications that run on such devices. Many developers are now designing applications that take advantage of the unique features of mobile devices, such as global positioning systems or GPS chips, accelerometers, and gyroscopes. An embedded GPS chip allows a mobile device to use satellites to determine its precise location on Earth. That functionality is especially useful in designing applications that provide navigation, for example, telling users which way to walk or drive, or perhaps directing them to nearby services such as restaurants. An accelerometer allows a mobile device to detect its orientation with respect to the ground and to detect certain other forces, such as tightening and shaking. In several computer games that employ accelerometers, players interface with the system not by using a mouse or a keyboard, but rather by tightening, rotating, and shaking the mobile device. Perhaps more a practical use of these features is found in augmented reality applications, which overlays information on a display of the current environment. It's difficult to imagine how equivalent applications could be developed on traditional laptops or desktop computer systems. To provide access to online services, mobile devices typically use either the IEEE standard 802.11 wireless or circular data networks. The memory capacity and the processing speed of mobile devices, however, are more limited than those of PCs. Whereas a smartphone or tablet may have 64 GB in storage, it's not uncommon to find 1 TB in storage on a desktop computer. Similarly, because power consumption is such a concern, mobile devices often use processors that are smaller, are slower, and offer fewer processing cores than processors found on traditional desktop and laptop computers. Two operating systems currently dominate mobile computing: the Apple iOS and the Google Android. iOS was designed to run on Apple iPhone and iPad mobile devices. Android powers smartphones and tablet computers available from many manufacturers. We examine these two mobile operating systems in further details in part 2. Third, the distributed systems. A distributed system is a collection of physically separate, possibly heterogeneous computer systems that are networked to provide users with access to the various resources that the system maintains. Access to a shared resource increases computation speed, functionality, data availability, and reliability. Some operating systems generalize network access as a form of file access with the details of networking contained in the network interface's device driver. Others make users specifically invoke network functions. Generally, systems contain a mix of two modes, for example, FTP and NFS modes. The protocols that create a distributed system can greatly affect that system's utility and popularity. A network, in the simplest terms, is a communication path between two or more systems. Distributed systems depend on networking for their functionality. Networks vary by the protocols used, the distance between nodes, and the transport media. TCP/IP is the most common network protocol, and it provides the fundamentals architecture of the internet. Most operating systems support TCP/IP protocols, including all the general purpose ones. Some systems support proprietary protocols to suit their needs. To an operating system, a network protocol simply needs an interface device, a network adapter, for example, with a device driver to manage it as well as software to handle data. These concepts are discussed throughout this text. Networks are characterized based on the distances between their nodes. A local area network or LAN connects computers within a room or building or a campus. A wide area network, WAN, usually links buildings, cities, or countries. A global company may have a WAN to connect its offices worldwide, for example. These networks may run one protocol or several protocols. The continuing advent of new technologies brings about new forms of networks. For example, a metropolitan area network, or MAN, could link buildings within a city. Bluetooth and 802.11 devices use wireless technology to communicate over a distance of several feet, in essence, creating a personal area network or PAN between a phone and a headset or a smartphone and a desktop computer. The media to carry networks are equally varied. They include copper wires, fiber standards, strands, and wireless transmissions between satellites, microwave dishes, and radios. When computing devices are connected to cellular phones, they create a network. Even very short range infrared communication can be used for networking. At a rudimentary level, whenever computers communicate, they use or create a network. These networks also vary in their performance and reliability. Some operating systems have taken the concept of networks and distributed systems further than the notion of providing network connectivity. A network operating system is an operating system that provides features such as file sharing across the network, along with a communication scheme that allows different processes on different computers to exchange messages. A computer running a network operating system acts autonomously from all other computers on the network, although it's aware of the network and is able to communicate with other networked computers. A distributed operating system provides a less autonomous environment. The different computers communicate closely enough to provide the illusion that only a single operating system controls the network. We cover computer networks and distributed systems in part 17. Now, fourth, the client server computing. PCs have become faster, more powerful, and cheaper. Designers have shifted away from centralized system architecture. Terminals connected to centralized systems are now being supplanted by PCs and mobile devices. Correspondingly, user interface functionality once handled directly by centralized systems is increasingly being handled by PCs, quite often through a web interface. As a result, many of today's systems act as server systems to satisfy requests generated by client systems. This form of specialized distributed system, called a client-server system, which has the general structure depicted in Figure 1.18. Now the Figure 1.18, which is the general structure of a client-server system, consists of server and network which connected with client desktop and client laptop and client smartphone and other client devices. Servers systems can be broadly categorized as compute servers and file servers. The compute server system provides an interface to which a client can send a request to perform an action, for example, route data. In response, the server executes the action and sends the results to the client. A server running a database that responds to client requests for data is an example of such a system. The file server system provides a file system interface where clients can create, update, read, and delete files. An example of such a system is a web server that delivers files to clients running web browsers. Fifth, the peer-to-peer computing. Another structure for a distributed system is the peer-to-peer or P2P system model. In this model, clients and servers are not distinguished from one another. Instead, all nodes within the system are considered peers, and each may act as either a client or a server, depending on whether it's requesting or providing a service. Peer-to-peer systems offer an advantage over traditional client-server systems. In a client-server system, the server is a bottleneck, but in a peer-to-peer system, services can be provided by several nodes distributed throughout the network. To participate in a peer-to-peer system, a node must first join the network of peers. Once a node has joined the network, it can begin providing services to and requesting services from other nodes in the network. Determining what services are available is accomplished in one of two general ways. One, when a node joins a network, it registers its service with a centralized lookup service on the network. Any node desiring a specific service first contacts with this centralized lookup service to determine which node provides the service. The remainder of the communication takes place between the client and the service provider. 2. An alternative scheme uses no centralized lookup service. Instead, a peer acting as a client must discover what node provides a desired service by broadcasting a request for the service to all the other nodes in the network. The node or nodes providing that service responds to the peer making the request. To support this approach, a discovery protocol must be provided that allows peers to discover services provided by other peers in the network. Figure 1.19 illustrates such a scenario. Now with figure 1.19, which is peer-to-peer system with no centralized service, are the clients connected with each others with the mesh technology as shown here in this picture. Peer-to-peer networks gained widespread popularity in late 1990 with several file sharing services, such as Napster, and Gontella that enabled peers to exchange files with one another. The Napster system used an approach similar to the first type described above. A centralized server maintained an index of all files stored on peer nodes in the Napster network, and the actual exchange of files took place between the peer nodes. The Contella system used a technique similar to the second type. A client broadcasted file requests to other nodes in the system, and nodes that could service the request responded directly to the client. The future of exchanging file remains uncertain because peer-to-peer networks can be used to exchange copyrighted materials, music, for example, anom- anonymously, and there are laws governing the distribution of copyrighted material. Notably, Napster ran into legal trouble for copyright infringement, and its services were shut down in 2001. Skype is another example of peer to peer computing. It allows clients to make voice calls and video calls and to send text messages over the internet using a technology known as voice over IP or VoIP. Skype uses a hybrid peer to peer approach. It includes a centralized login server, but it also incorporates decentralized peers and allows two peers to communicate. Six, the virtualization technology. Virtualization is a technology that allows operating systems to run as applications within other operating systems. At first blush, there seems to be little reason for such functionality, but the virtualization industry is vast and growing, which is a testament to its utility and importance. Broadly speaking, virtualization is one number of a class of software that also includes emulation. Emulation is used when the source CPU type is different from the target CPU type. For example, when Apple switched from the IBM Power CPU to the Intel x86 CPU for its desktop and laptop computers, it included an emulation facility called Rosetta, which allowed applications compiled for the IBM CPU to run on the Intel CPU. That same concept can be extended to allow an entire operating system written for one platform to run on another. Emulation comes at a heavy price, however. Every machine level instruction that runs natively on the source system must be translated to the equivalent function on the target system, frequently resulting in several target instructions. If the source and target CPUs have similar performance levels, the emulated code can run much slower than the native code. A common example of emulation occurs when a computer language is not compiled to native code, but instead is either executed in its high level form or translated to an intermediate form. This is known as interpretation. Some languages, such as BASIC, can be either compiled or interpreted. Java, in contrast, is always interpreted. Interpretation is a form of emulation, in that the high level language code is translated into native CPU instructions, emulating not another CPU but a theoretical virtual machine on which that language could run natively. Thus, we can run Java programs on Java virtual machines, but technically, those virtual machines are Java emulators. With virtualization, in contrast, an operating system that is natively compiled for a particular CPU architecture runs within another operating system also native to that CPU. Virtualization first came about on IBM mainframes as a method for multiple users to run tasks concurrently. Running multiple virtual machines allowed and still allows many users to run tasks on a system designed for a single user. Later, in response to problems with running multiple Microsoft Windows XP applications on the Intel x86 CPU, the VMware company created a new virtualization technology in the form of an application that ran on XP. That application ran one or more guest copies of Windows or other native x86 operating systems, each running its own applications. Now we see the figure 1.20. Figure 1.20 is a virtualization technology, where at the left side, the real device, which consists of processes and one kernel and one hardware. On it, we can make a multiple virtual machines such as at right side, the programming interface, which includes VM1 and VM2 and VM3, which are three virtual machines. Each virtual machine has its kernel and its processes. The three virtual machines have one virtual machine manager, and they are all on the same hardware. Windows was the host operating system, and the VMware application was the virtual machine manager VMM. The VMM runs the guest operating systems, manages their resource use, and protects each guest from the others. Even though modern operating systems are fully capable of running multiple applications reliably, the use of virtualization continues to grow. On laptops and desktops, a VMM allows the user to install multiple operating systems for exploration or to run applications written for operating systems other than the native host. For example, an Apple laptop running Mac OS X on the x86 CPU can run a Windows guest to allow execution of Windows applications. Companies writing software for multiple operating systems can use virtualization to run all of those operating systems on a single physical server for development and for testing and debugging within data centers. Virtualization has become a common method of executing and managing computing environments. The VMMs like VMware ESX and Critics Zen Server no longer run on host operating systems, but rather are the hosts. Full details of the features and implementation of virtualization are found in Part 16. Seventh, the cloud computing. Cloud computing is a type of computing that delivers computing, storage, and even applications as a service across a network. In some ways, it's a logical extension of virtualization because it uses virtualization as a base for its functionality. For example, the Amazon Elastic Compute Cloud EC2 facility has thousands of servers, millions of virtual machines, and petabytes of storage which are available for using by anyone on the internet. Users pay per month based on how much of those resources they use. There are actually many types of cloud computing, including the following: one, public cloud, which is a cloud available via the internet to anyone willing to pay for the services. Two, private cloud, which is a cloud run by a company for that company's own use. Three, hybrid cloud, a cloud that includes both public and private cloud components. Software as a service or SaaS is one or more applications such as word processors or spreadsheets available via the internet. Platform as a service or PaaS, a software stack ready for application use via the internet, for example, a database server. The infrastructure as a service or IaaS, servers or storage available over the internet, for example, storage available for making backup copies of production data. These cloud computing types are non discrete, as a cloud computing environment may provide a combination of several types. For example, an organization may provide both SaaS and IaaS as a publicly available service. Certainly, there are traditional operating systems within many of the types of cloud infrastructure. Beyond those are the VMMs that manage the virtual machines in which the user processes run. At a higher level, the VMMs themselves are managed by cloud management tools such as VMware Cloud Director and the open source Eucalyptus toolset. These tools manage the resources within a given cloud and provide interfaces to the cloud components, making a good argument for considering them a new type of operating system. Figure 1.21, which is shown here, illustrates a public cloud providing IaaS service. Notice that both the cloud services and the cloud user interface are protected by a firewall. In this figure, which shows the cloud computing, it consists of the internet and firewall and a load balancer. The load balancer is connected with a cloud management services and a storage and a servers which holds virtual machines. All these components are managed by the cloud managed services that at right side. The user or the customer requests from the internet through the cloud customer interface, which is dealing with the cloud management services, as shown here. Eighth, real-time embedded systems. The embedded computer are the most prevalent form of computers in existence. These devices are found everywhere, from car engines and manufacturing robots to DVDs and microwave ovens. They tend to have very specific tasks. The systems they run on are usually primitive, and so the operating systems provide limited features. Usually, they have little or no user interface, preferring to spend their time monitoring and managing hardware devices, such as automobile engines and robotics arms. These embedded systems vary considerably. Some are general purpose computers running standard operating systems such as Linux, with special purpose applications to implement the functionality. Others are hardware devices with a special purpose embedded operating system providing just the functionality desired. Yet others are hardware devices with application specific integrated circuits, ASICs, that perform their tasks without an operating system. The use of embedded systems continues to expand. The power of these devices, both as standalone units and as elements of networks and the web, is sure to increase as well. Even now, entire houses can be computerized so that a central computer, either a general purpose computer or an embedded system, can control heating and lighting, alarm systems, and even coffee makers. Web access can enable a homeowner to tell the house to heat up before she arrives home. Someday, the refrigerator can notify the grocery store when it notices that the milk is gone. Embedded systems almost always run real-time operating systems. A real-time system is used when rigid time requirements have been placed on the operation of a processor or the flow of data. Thus, it's often used as a control device in a dedicated application. Sensors bring data to the computer. The computer must analyze the data and possibly adjust controls to modify the sensor inputs. Systems that control scientific experiments, medical imaging systems, industrial control systems, and certain display systems are real time systems. Some automobile engine fuel injection systems Home appliance controllers and weapon systems are also a real-time systems. A real-time system has well-defined fixed-time constraints. Processing must be done within the defined constraints, or the system will fail. For instance, it wouldn't do for a robot arm to be instructed to halt after it had smashed into the car it was building. A real time system functions correctly only if it returns the correct result within its time constraints. Contrast this system with a time sharing system, where it's desirable but not mandatory to respond quickly, or a patch system, which may have no time constraints at all. In part 6, we consider the scheduling facility needed to implement real time functionality in an operating system. In part 9, we will describe the design of memory management for real time computing. Finally, in part 18 and 19, we describe the real time components of the Linux and Windows 7 operating systems. Now, the open source operating systems. We noted at the beginning of this chapter that the study of operating systems has been made easier by the availability of a vast number of open source releases. Open source operating systems are those available in source code format rather than as compiled binary code. Linux is the most famous open source operating system, while Microsoft Windows is a well known example of the opposite closed source approach. Apple's Mac OS X and iOS operating systems comprise a hybrid approach, where they contain an open source kernel named Darwin, yet include proprietary closed source components as well. Starting with the source code allows the programmer to produce binary code that can be executed on a system. Doing the opposite, reverse engineering the source code from the binaries, is quite a lot of work, and useful items such as comments are never recovered. Learning operating systems by examining the source code has other benefits as well. With the source code in hand, a student can modify the operating system and then compile and run the code to try out those changes, which is an excellent learning tool. This text includes projects that involve modifying operating system source code, while also describing algorithms at a high level to be sure all important operating system topics are covered. Throughout the text, we provide pointers to examples of open source code for deeper study. There are many benefits to open source operating systems, including a community of interested and usually unpaid programmers who contribute to the code by helping to debug it, analyze it, provide support, and suggest changes. Arguably, open source code is more secure than closed source code because many more eyes of developers are viewing the code. Certainly, open source code has bugs, but open source advocates argue that bugs tend to be found and fixed faster owing to the number of people using and viewing the code. Companies that earn revenue from selling their programs often hesitate to open source their code. But Red Hat and a myriad of other companies are doing just that and showing that commercial companies benefit rather than suffer when they open source their code. Revenue can be generated through support contracts and the sale of hardware on which the software runs, for example. The open source operating systems. First, the history. In the early days of modern computing, that's 1950, a great deal of software was available in open source format. The original hackers, computer enthusiasts at MIT Tech Model Railroad Club left their programs in drawers for others to work on. Homebrew user groups exchanged code during their meetings. Later, company-specific user groups such as Digital Equipment Corporation's DEC accepted contributions of source code programs, collected them onto tabs, and distributed the tabs to interested members. Computer and software companies eventually sought to limit the use of their software to authorized computers and paying customers, releasing only the binary files compiled from the source code rather than the source code itself, which helped them to achieve this goal, as well as protecting their code and their ideas from their competitors. Another issue involved copyrighted material. Operating systems and other programs can limit the ability to play back movies and music or display electronic books to authorized computers. Such copy protection or digital rights management (DRM) wouldn't be effective if the source code that implemented these limits were published. Laws in many countries, including the US Digital Millennium Copyright Act (DMCA), make it illegal to reverse engineer DRM code or otherwise try to circumvent copy protection. To counter the move to limit software use, the redistribution Richard Stallman in 1983 started the GNU project to create a free open source Unix compatible operating system. In 1985, he published the GNU Manifesto, which argues that all software should be free and open sourced. He also formed the Free Software Foundation (FSF) with the goal of encouraging the free exchange of software source code and the free use of that software. Rather than copyright its software, the FSF copylifts the software to encourage sharing and improvement. The GNU General Public License or GPL codifies copylifting and is a common license under which free software is released. Fundamentally, GPL requires that the source code be distributed with any binaries and that any changes made to the source code be released under the same GPL license. Second, with the Linux operating system. As an example of an open source operating system, consider the GNU Linux project. The GNU project produced many Unix compatible tools, including compilers, editors, and utilities, but never released a kernel. In 1991, a student in Finland, Linus Torvalds, released a rudimentary Unix-like kernel using the GNU compilers and tools, and invited contributions worldwide. The advent of the internet meant that anyone interested could download the source code, modify it, and submit changes to Torvalds. Releasing updates once a week allowed this so-called Linux operating system to grow rapidly, enhanced by several thousand of programmers. The resulting GNU Linux operating system has spawned hundreds of unique distributions or custom builds of the system. Major distributions include Red Hat, SUSE, Fedora, Debian, Slackware, and Ubuntu. Distributions vary in function, utility, installed applications, hardware support, user interface, and the purpose. For example, Red Hat Enterprise Linux is geared to large commercial use. BCL Linux OS is a live CD, an operating system that can be booted and run from a CD-ROM without being installed on a system's hard disk. One variant of BCL Linux OS called BCL Linux OS Super Grammar DVD, Super Gamer DVD, which is a live DVD that includes graphics, drivers, and games. A gamer can run it on any compatible system simply by booting from the DVD. When the gamer is finished, a reboot of the system resets it to its installed operating system. You can run Linux on a Windows system using the following simple free approach. First, download the free VMware Player tool from www.vmware.com/download/player and install it on your system. Second, choose a Linux version from among the hundreds of appliances or virtual machine images available from VMware at http://www.vmware.com/appliances. These images are pre-installed without operating systems and applications and include many flavors of Linux. Put the virtual machine within VMware Player. With this text, we provide a virtual machine image of Linux running the Debian release. This image contains the Linux source code as well as tools for software development. We will cover examples involving the Linux image throughout this text, as well as a detailed in-case study in, in Part 18. Third, the BSD Unix system. The BSD Unix has a longer and more complicated history than Linux. It started in 1978 as a derivative of AT&T Unix system. Releases from the University of California at Berkeley, UCB, came in source and binary form, but they weren't open source because a source and binary form a license from AT&T was required. BSD Unix development was slowed by a lawsuit by AT&T, but eventually a fully functional open source version 4.4 BSD Lite was released in 1994. Just as with Linux, there are many distributions of BSD Unix, including the FreeBSD, NetBSD, OpenBSD, and Dragonfly BSD. To explore the source code of FreeBSD, simply download the virtual machine image of the version of interest and boot it within VMware as described above for Linux. The source code comes with the distribution and is stored in /usr/src directories. The kernel source code is in /user/source/sys. For example, to examine the virtual memory implementation code in the FreeBSD kernel, see the files in the path user/source/sys/vm. Darwin, the core kernel component of Mac OS X, is based on BSD Unix and is open sourced as well. That source code is available from http://www.opensource.apple.com. Every Mac OS X release has its open source components posted at that site. The name of the package that contains the kernel begins with Xeno or XNU. Apple also provides extensive developer tools, documentation, and support at http://connect.apple.com. For more information, see Appendix A in the bibliography. Fourth, the Solaris operating system. Solaris is the commercial Unix-based operating system of Sun Microsystems. Originally, Sun OS operating system was based on BSD Unix. Sun moved to AT&T Systems v Unix as its base in 1991. In 2005, Sun open sourced most of the Solaris code as the Open Solaris project. The purchase of Sun by Oracle in 2009, however, left the state of this project unclear. The source code as it was in 2005 is still available via a source code browser and for download at http://src.opensolaris.org/source. Several groups interested in using open source have started from that base and extended its features. Their working set is Project Elimus, which has expanded from the open source base to include more features and to be the basis for several products. Elimus is available at http://wiki.elimus.org. Fifth, the open source systems as learning tools. The free software movement is driving legions of programmers to create thousands of open source projects, including operating systems. Sites like http://freshmeat.net and http://destrowatch.com provide portals to many of these projects. As we stated earlier, open source projects enable students to use source code as a learning tool. They can modify programs and test them, help find and fix bugs, and otherwise explore matter. Full featured operating systems, compilers, tools, user interfaces, and other types of programs. The availability of source code for historic projects such as Multics can help students to understand those projects and to build knowledge that will help in the implementation of new projects. GNU Linux and BSD Unix are all open source operating systems, but each has its own goals and utility, license, and purpose. Sometimes licenses are not mutually exclusive and cross pollination occurs, allowing rapid improvements. In operating system projects, for example, several major components of open source have been ported to BSD Unix. The advantages of free software and open sourcing are likely to increase the number and quality of open source projects, leading to an increase in the number of individuals and companies that use these projects. Summary: the operating system is a software that manages the computer hardware as well as providing an environment for application programs to run. Perhaps the most visible aspect of an operating system is the interface to the computer system it provides to the human user. For a computer to do its job of executing programs, the programs must be in main memory. Main memory is the only large storage area that the processor can access directly. It's an array of bytes ranging in size from millions to billions. Each byte in memory has its own address. The main memory is usually a volatile storage device that loses its contents when power is turned off or lost. Most computer systems provide secondary storage as an extension of main memory. Secondary storage provides a form of non volatile storage that is capable of holding large quantities of data permanently. The most common secondary storage device is a magnetic disk, which provides storage of both programs and data. The wide variety of storage systems in a computer system can be organized in a hierarchy according to speed and cost. The higher levels are expensive, but they are fast. As we move down the hierarchy, the cost per bit generally decreases, whereas the access time generally increases. There are several different strategies for designing a computer system. The single processor systems have only one processor, while multiprocessor systems contain two or more processors that share physical memory and peripheral devices. The most common multiprocessor design is symmetric multiprocessing or SMP, where all processors are considered peers and run independently of one another. Clustered systems are a specialized form of multiprocessor systems and consist of multiple computer systems connected by a local area network. To best utilize the CPU, modern operating systems employ multiprogramming, which allows several jobs to be in memory at the same time, thus ensuring that the CPU always has a job to execute. Time-sharing systems are an extension of multi-programming, wherein CPU scheduling algorithms rapidly switch between jobs, thus providing the illusion that each job is running concurrently. The operating system must ensure correct operation of the computer system to prevent user programs from interfering with the proper operation of the system. The hardware has two modes, user mode and kernel mode. Various instructions, such as the input-out instructions and halt instructions, are privileged and can be executed only in the kernel mode. The memory in which the operating system resides must also be protected from modification by the user. A timer prevents infinite loops. These facilities, dual mode, privilege instructions, memory protection, and timer interrupt are basic building blocks used by operating systems to achieve correct operation. A process or job is a fundamental unit of work in an operating system. Process management includes creating and deleting processes and providing mechanisms for processes to communicate and synchronize with each other. An operating system manages memory by keeping track of what parts of memory are being used and by whom. The operating system is also responsible for dynamically allocating and freeing memory space. The storage space is also managed by the operating system. This includes providing file systems for representing files and directories and managing space on mass storage devices. Operating systems must also be concerned with protecting and securing the operating systems and users. Protection measures control the access of processes or users to the resources made available by the computer system. Security measures are responsible for defending a computer system from external or internal attacks. Several data structures that are fundamental to computer science are widely used in operating systems, including lists, stacks, queues, trees, hash functions, maps, and bitmaps. Computing takes place in a variety of environments. Traditional computing involves desktop and laptop PCs usually connected to a computer network. Mobile computing refers to computing on handheld smartphones and tablet computers, which offer several unique features. Distributed systems allow users to share resources on a geographically dispersed hosts connected via a computer network. Services may be provided through either the client server model or the peer to peer model. Virtualization involves abstracting a computer's hardware into several different execution environments. Cloud computing uses a distributed system to abstract services into a cloud, where users may access the services from remote locations. Real-time operating systems are designed for embedded environments, such as consumer devices, automobiles, and robotics. The free software movement has created thousands of open source projects, including operating systems. Because of these projects, students are able to use source code as a learning tool. They can modify programs and test them, help find and fix bugs, and otherwise explore matter, full-featured operating systems, compilers, tools, user interfaces, and other types of programs. Geno Genolix project and BSD Unix systems are open source operating systems. The advantages of free software and open sourcing are likely to increase the number and the quality of open source projects, leading to an increase in the number of individuals and companies that use these projects. Now, with the practice exercises. First exercise: what are the three main purposes of an operating system? Second, we have stressed the need for an operating system to make efficient use of the computing hardware? When is it appropriate for the operating system to forsake this principle and to waste resources? Why is such a system not really wasteful? Number three, what is the main difficulty that a programmer must overcome in writing an operating system for a real time environment? 4. Keeping in mind the various definitions of operating system. Consider whether the operating system should include applications such as web browser and mail programs. Argue both that it should and that it shouldn't, and support your answers. Exercise 5. How does the distinction between kernel mode and user mode function as a rudimentary form of protection security for the system? Exercise 6. Which of the following instructions should be privileged? A. Set value of timer. B. Read the clock. C. Clear memory. D. Issue a trap instruction. E. Turn off interrupts. F. Modify entries in a device status table. G. Switch from user to kernel mode. H. Access input output device. Exercise 1.7. Some early computers protected the operating system by balancing it in a memory partition that couldn't be modified by either the user job or the operating system itself. Describe two difficulties that you think could arise with such a scheme. Exercise 1.8. Some CPUs provide for more than two modes of operation. What are two possible uses of these multiple modes? 1.9. Timers could be used to compute the current time. Provide a short description of how this could be accomplished. Exercise 1.10. Give two reasons why caches are useful. What problems do they solve? What problems do they cause? If a cache can be made as large as the device for which it's caching, for instance, a cache as large as a disk, why not make it that large and eliminate the device? Exercise 11. Distinguish between the client server and peer to peer models of distributed systems. Exercise 12. In a multi-programming and time-sharing environment, several users share the system simultaneously. This situation can result in various security problems. A. What are two such problems? B. Can we ensure the same degree of security in a time-shared machine as in a dedicated machine? Explain your answer. Exercise 13. The issue of resource utilization shows up in different forms in different types of operating systems. List what resources must be managed carefully in the following settings. A. Mainframe or mini computer systems. B. Workstations connected to servers. C. Mobile computers. Exercise 14. Under what circumstances would a user be better off using a time sharing system than a PC or a single user workstation? Exercise 15. Describe the differences between symmetric and asymmetric multiprocessing. What are three advantages and one disadvantage of multiprocessor systems? 1.16. How do cluster systems differ from multiprocessor systems? What is required for two machines belonging to a cluster to cooperate to provide a highly available service? Exercise 1.17. Consider a computing cluster consisting of two nodes running a database. Describe two ways in which the cluster software can manage access to the data on the disk. Discuss the benefits and disadvantages of each. 1.18. How are network computers different from traditional personal computers? Describe some usage scenarios in which it's the advantageous to use network computers. Exercise 1.19. What is the purpose of interrupts? How does an interrupt differ from a trap? Can traps be generated intentionally by a user program? If so, for what purpose? Exercise 20. Direct memory access is used for high speed input output devices in order to avoid increasing the CPU's execution load. A. How does the CPU interface with the device to coordinate the transfer? B. How does the CPU know when the memory operations are complete? C. The CPU is allowed to execute other programs while the DMA controller is transferring data. Does this process interfere with the execution of the user programs? If so, describe what forms of interference are caused. Exercise 21. Some computer systems don't provide a privileged mode of operation in hardware. Is it possible to construct a secure operating system for these computer systems? Give arguments both that it's and that it's not possible. Exercise 122. Many SMP systems have different levels of caches. One level is local to each processing core, and another level is shared among all processing cores. Why are caching systems designed this way? Exercise 1.23. Consider an SMP system similar to the one shown in figure 1.6. Illustrate within, with an example how data residing in memory cloud could in fact have a different value in each of local caches. Exercise 24. Discuss with examples how the problem of maintaining coherence of cached data manifests itself in the following processing environments. A. Single processor systems. B. Multiprocessor systems. C. Distributed systems. Exercise 25. Describe a mechanism for enforcing memory protection in order to prevent a program from modifying the memory associated with other programs. Exercise 1.26. Which network configuration LAN or WAN would best suit the following environments? A. A campus student union. B. Several campus locations across a statewide university system. C. A neighborhood. Exercise 27. Describe some of the challenges of designing operating systems for mobile devices compared with designing operating systems for traditional PCs. Exercise 128. What are some advantages of peer-to-peer systems over client-server systems? 1.29. Describe some distributed applications that would be appropriate for a peer-to-peer system. 1.30. Identify several advantages and several disadvantages of open source operating systems. Include the types of people who would find each aspect to be an advantage or a disadvantage. Now with the graphical notes. Brookshire 2012 provides an overview of computer science in general. Through coverage of data structures can be found in Corman et al. 2009. Russinovich and Solomon 2009 give an overview of Microsoft Windows and covers considerable technical detail about the system internals and components. McDougall and Marrow 2007 cover the internals of the Solaris operating system. Mac OS internals are discussed in Sign 2007 and Lab 2010, which provides an overview of the Linux operating system and great detail about data structures used in the Linux kernel. Many general text box cover operating systems including Stallings 2011, Detail ETAL 2004, and Tenenbaum 2007. Kurtz and Rose 2013 provides a general overview of computer networks, including a discussion of client-server and peer-to-peer systems. Tarcoma and Larger Space 2011 examines several different mobile operating systems, including Android and iOS. Hensey and Patterson 2012 provide coverage of input-output systems and buses, and of system architecture in general. Bryant and O'Halloran 2010 provide a thorough overview of a computer system from the perspective of computer programmer. Details of the Intel 64 instruction set and the privilege mode can be found in Intel 2011. The history of open sourcing and its benefits and challenges appears in Raymond 1999. The Free Software Foundation has published its philosophy in http://www.geno.org philosophy/free software for freedom.html. The open source of Mac OS are available from the http://www.apple.com/open source. Wikipedia has an informative entry about the contributions of Richard Stallman at http://en.wikipedia.org/wiki/Richard Stallman. The source code of Maltex is available at http://web.met.edu/maltex-history/source/maltex internet servers/maltex sources.html. Brookshire 2012 J.G. Brookshire Computer Science An Overview 11th edition. Edition Wesley 2012. Brent and Halloran 2010 R. Brent and D. O. Halloran Computer Systems, A Programmer's Perspectives, 2nd edition. Edition Wesley 2010. Corman ETAL 2009 TH Corman CE Laseron RL Revest and C. Sten Introduction to Algorithms, 3rd edition. MIT Press 2009. Detail it AL 2004 H Detail B Detail and D. Kovnes Operating Systems, 3rd edition. Prentice Hall 2004. Hensey and Patterson 2012 J. Hensey and D. Patterson Computer Architecture, A Quantitative Approach, 5th edition. Morgan Kaufman 2012. Intel 2011 Intel 64 and IA32 Architecture Software Developers Manual Combined Volumes 1, 2A, 2B, 3A, and 3B. Intel Corporation 2011. Kurtz and Rose 2013. J. Kurose and K. ROSS Computer Networking, A Top-Down Approach, 6th edition. Edition Wesley 2013. Love 2010. R. Love Linux Kernel Development, 3rd edition. Developers Library 2010. MC Dougal and Mero 2007. R.MC Dougal and J. Mero Solaris Internals, 2nd edition. Prentice Hall 2007. Raymond 1999. E.S. Raymond The Cathedral and the Bazaar, O'Reilly and Associates, 1999. Rushenve and Solomon 2009, ME Rushenve and DA Solomon, Windows internals, including Windows Server 2008 and Windows Vista. 5th edition, Microsoft Press 2009. Sin 2007, ASIN, Mac OS internals, A Systems Approach Edition, Wesley 2007, Stalin's 2011, Stalin's Operating Systems 7th edition, Prentice Hall 2011, Tan Tenenbaum 2007, Tenenbaum Modern Operating Systems 3rd edition, Prentice Hall 2007, Tarkuma and Large Bits 2011, Tarkuma and Large Bits, Archiving over the Mobile Computing Chasm, Platforms and Runtimes, IEEE Computer, Volume 44, 2011, page 22 to 28.